My talk today is entitled Carbon Estimation Methods, approaches, methods commonly used to estimate carbon within forest, and this can be part of a national forest inventory to have some idea of the amount of carbon sequestered at a regional or national level or even statewide level or county level. It can be part of a particular company. They want to know their carbon footprint, how much are they offsetting with their forest. And then there's often these carbon offset markets that allow landowners to that are sequestering carbon in their forest, an additional amount of carbon sequestered or stored or removed from the atmosphere resulting from the growth of their forest, that allows then for the compensation or offset of emissions, greenhouse gas emissions or CO2 emissions made by an industry located somewhere else. And of course, there's a variety of ways that these projects can result in additional amounts of sequestration, but these provide an additional source of revenue. So of course they need some way to quantify the amount of carbon, the baseline amount as well as an additional amount, to have some idea of what payment should be received. And so here's a business as usual, kind of what would a landowner do typically. This is just an example for Loblolly pine plantations here in the southeast. You plant at year 0. As plantation grows, you start getting intense competition for light, moisture, and nutrients. You're going to thin 15, then again at 21, and then final clear cut at age 28. Remember, this is just an example. There's many other forest management regimes for these plantations, and there's many other forest types. But what is the carbon being sequestered in this forest? Carbon definitely is being sequestered or stored or removed from the atmosphere through this forest. How much is that? Where is that carbon located? Below ground, above ground? Is it located in the crown branches and the leaves and the stem, merchantable stem, the upper stem? So we need ways to quantify this, and then this will provide us some baseline, and then we need a way to quantify an additional amount of carbon being sequestered. So for instance, there was a forest carbon market, NCX, that allowed for landowners to receive compensation for carbon sequestered resulting directly from a 1-year deferral, harvest deferral, resulting directly from them enrolling into NCX and thereby deferring a harvest for 1 year. And by deferring that, there was an additional amount of carbon being sequestered on the landscape, being stored on the landscape. So how much is that additional amount? What's the baseline amount? How much should that landowner be compensated? How much are they losing financially? So there's these things that we need to do to quantify the amount of carbon being sequestered in these forests, as well as even say things like the amount of carbon being removed. If we harvest trees or we remove a forest and put it into some type of other land use, agriculture or a mall or a residential area, how much carbon is being removed? Then we get into the question of why do we conduct inventories? And as I go through here, kind of think about this. So inventories help to determine the amount of a resource. How much is out there? Where's the spatial distribution of that resource? That helps to specify what activities need to occur to meet a management objective, for example. So it's not just an appraisal. And my point here, everybody, to me, when we're measuring carbon, we're really doing nothing differently than what we've been doing for years on traditional timber inventories, and then even multiple resource inventories, right? Understory vegetation, below ground biomass, or say for timber, just the above ground merchantable stem. Nothing different in my opinion. We're going to run off of diameter and height. Same thing with volume equations. We were estimating volume using equations, and now we're just going to take that a step further. Then we're going to multiply by some multiplier to get carbon. I don't think we ever measure carbon directly in a forest. This is basically the same question we've been asking for years on traditional timber inventories. What's the amount of timber in cubic feet or board feet or tons? Where's the spatial distribution for a logger? But now we're going to think about it a little bit differently maybe. Where's the spatial distribution on a landowner's property for things like leakage? Or, to me, nothing different. What's the economic value of that timber, the amount of tons out there? How much saw log, pulpwood, and chipping saw is out there? No different, right? Where's that carbon? In the below ground, above ground, in the crown, in the stem? What's the potential restrictions when harvesting, right? It's often part of the probability of what's the risk of this carbon being removed from the landscape due to harvesting, or what's the risk of this carbon being removed because they're going to sell this property to somebody else, and therefore we don't want that property to be sold, so we're going we're going to pay that landowner to keep that. And landscape level resource planning. To me, my point here, everybody, this is nothing different than what we've been talking about for years. And so then we get into what are you willing to buy and sell on? So what is an inventory? Well, to me, everybody, I've taught measurements for several years. I've done many resource measurement projects across the U.S. To me, an inventory is anything you're willing to sell on or buy on, and anything that the other party's willing to buy and sell on. Right? I know a lot of friends of mine with pulpwood at $2 to $5 a ton. They'll just drive by the forest. They don't even put boots in the ground inventories. Due to the air involved, the amount of money lost or gained is not worth the amount of cost involved in conducting like an inventory that's a percent cruise or meets some standard air, meets some level of precision. Same thing with carbon. Things like CCX had boots on the ground. I think they had a lot more field-based inventory protocols. But NCX, what were they doing? They were running off of satellite imagery paired with FIA data, right? The value of that carbon is not the value of a bird's eye sugar maple at $50,000 a board, 1,000 board feet, or black walnut or black cherry, right? Even loblolly pine saw logs. What's the value of that based on the amount of inventory intensity? Same question we've been asking for years with timber inventories and multiple resource inventories. So we're always going to want to know this information at the lowest cost and the least amount of time. Once again, everybody, NCX's base map, land yield, I think is another one with core carbon. Getting this information, unlike CCX, where I think the landowners had to pay for the inventory, now it's basically free. The inventory is free to the landowner. Now, what's the amount of air involved? What's the amount of air in the business as usual assessment? What's that air? Well, the buyer and the seller, they need to accept that level of air given the amount of cost being spent on the inventory. So obviously people are willing to accept that air, right? You could have a lot more detailed inventory, but then all of a sudden the carbons are really not worth it given the value of the inventory. Anyway, it's all about 100% tally. Okay, so there's no sampling. So as far as I know, there's two main types of air when you're conducting inventories or you're measuring something. There's sampling air, which results from measuring a reduced portion of the population. First, you have to define the population, the amount of carbon above ground. Carbon, okay, I'm not measuring below ground, just above ground, and it's only in the pine. Or it's hardwood and just hardwood, or it's all species. Is it understory vegetation or not, right? So I have to define that population first. And then, can I do 100% tally? Well, once again, it's going to come back to the value of that timber. Now, I can see the days where maybe we're going to have different valued carbon, almost like black walnut saw logs versus loblolly pine saw logs. Redwood carbon may become so valuable that we're willing to spend a lot more money on inventorying that. We want to know how much we're gaining or losing, but loblolly pine carbon is not, the value there, that we have a lot of it, it's not really that valuable per unit. So therefore we're willing to accept more air there. I could see that, right? Or bottom and hardwoods or something may become more valuable. That carbon on a per unit basis may become more valuable, justifying a higher inventory cost. Okay, but we're going to measure a reduced portion, and then we're going to infer, or hopefully that reduced portion is representative of the rest of the population that we're not measuring. That's sampling air. Then we have measurement air. Okay, the tree height was 75 feet, but I measured it to be 70 feet. Or the diameter was 10.2, but I put it in as 10 in the volume equation. What's the air involved in the satellite imagery? Right? Maybe the reflectance wasn't exactly the best for me to determine the nature of what I'm measuring from a distance, or maybe the satellite imagery is not the resolution that I want, or maybe the volume equation is not the best volume equation. It's it's one from the Atlantic coastal plain, but I'm using it out here in the Western Gulf because for that Shumard oak, there's no other volume equation available. So to me, that's kind of the measurement air. But the sampling air, right? We're going to measure a reduced portion, so we can look at this plantation here. Actually, it's got two stands. It's got a kind of a mixed pine, but we're just going to say it's one plantation. Okay, it's just so once again, what's that air involved there, right? But I can't measure every tree out here. The value of the carbon or even timber. All right, saw logs, chip and saw is not really worth it, so I'm going to what? I'm going to measure a reduced portion. So I'm going to measure these 4 plots, rectangular plots. Here they are. And I'm going to do what? I'm going to measure them, and I'm going to infer that they're representative. I'm hoping they're representative of the rest of this population, and then I'm going to take the measurements here, summarize them, and then infer that that's the rest, that represents the rest. Once again, everybody, what's the error involved in that? What's the value of the resource? Nothing different than what we've been doing for years. And this is what I'm getting at. The carbon here may not be worth it. Okay, this may be fine, but like I said, like a redwood carbon or something like that, you may even do 100% tally on some of those forests. I don't know, because of the value of that resource. That carbon on a per unit basis may be higher. Generally, right, the greater the sample of a stand, the better the estimate should be on average. Now, when I go from 100 observations to 10,000 observations, usually my error is not going to go up. It's usually going to go down. I'm going to get more precise. And why? Because once again, same thing with carbon, same thing with timber, same thing with understory vegetation, same thing with wildlife assessments. If I sample a little bit of the population, I may sample all the small parts, or I may sample all the large parts, because I'm just sampling a small part. Now, probability may not be that high of that, but I could. What happens if I measure more and more of the population? The more and more I measure, the more and more, what's the probability that I'm going to measure only the large part, only the small part, right? I increase, that's one large reason why the precision should increase as I measure a greater sample size. That probability of measuring the outliers, the impacts of the outliers is reduced. Same thing with carbon, right? The more of a forest I measure, the better my estimate should be. So we can have boots on the ground. Here's my population. And let's say I want to measure both above ground and below ground. Okay, so I'm going to go out and I'm going to measure some plots. Boots on the ground. I'm going to randomly locate these plots. Don't pay any attention to the black here, okay? Or I can do as a traditional timber inventory, I'm going to do a systematic grid. Okay, because I want to ensure that all my plots aren't down here randomly, or all my plots are up here if I locate them randomly. But I can spatially locate them myself, but then, right, I may introduce some bias into that. Nothing new, you guys, in what we've been doing for traditional inventories. And then what? I'm going to go out to that plot and I'm going to measure diameter and I'm going to measure height. And traditionally what we've been doing, I get the diameter and the height and I put them into a volume equation. And then I measure volume. What makes sense if I'm going to cut the trees down to measure carbon, because I'm going to buck them up into these little sections and measure the carbon. I've kind of defeated the idea of carbon sequestration, the idea of carbon storage. We're going to use volume equations, dry weight equations, based in a research setting where they've actually kind of done a little more intensive sampling. Then I'm going to create these equations, estimate those parameters in those research settings, and then bring them back operationally and estimate the amount of carbon in this tree based on these equations. So here's d squared h. Diameter squared h for volume. Well, that makes sense. D squared is what? Area. That's 2 dimensions, so that's your area. 8.0054545154 times d squared for the English metric. I forget what it is off the top of my head. I'm going to multiply that by h, the total tree height or merchantable height, right? The 3rd dimension. Okay, so these equations make sense, but a lot of these times we can then we're going to measure volume and then convert over to dry weight based on things like specific gravity and then pounds per cubic foot, dry weight or green weight. And then you're often going to assume half of the dry weight is carbon. And that's how we get these equations. And then we're going to sum that up to plot level or variable radius point, 3p, and then I'm going to blow it up to the population. But here, you guys, there's actually a case where they measured weight, right? This is a research setting in Arkansas. How often do you see this operationally? They may take a truckload and then scale it at the mill. But once again, you're not really going to do that for carbon. I don't want to cut the tree down and kind of defeat the purpose of carbon sequestration. So to me, everything's still running off of essentially diameter and height. Even the remote sensing methods, you guys, are going to run off of some type of boots on the ground, running off of diameter and height. Nothing new than what we've been doing for years. And so, as I said, we're going to estimate dry weight. Eventually, we're going to estimate dry weight with these equations, usually based on height and diameter. And even when you're using remote sensing like LiDAR or satellite imagery, but LiDAR, right? You got that pulse, the amount of time hits that tree. That's the height, the amount of time back. My understanding, everybody. And then what? I'm gonna predict diameter as a function of height. And now I have my height and my predicted diameter. Then I'm going to predict volume or dry weight based on these equations. So everything is going to come back somehow to diameter and height. Nothing new. As far as I know right now, we're not measuring carbon directly. And then we're going to assume that dry weight, that 50% of that dry weight is carbon. So again, what's the air involved and what's the measurement air involved in that? Certain species may be 0.48 or 0.52, like hardwoods versus pine. But we're all willing to buy and sell on that amount of air. And then we're going to convert over to CO2 equivalent metric tons. And hopefully I'm doing this right. So I got 44 divided by 12. Well, where's 44? Right, I believe it's the atomic weight or the mass. Okay, you chemistry folks can correct me. Oxygen, I have 2. CO2, so that's 16 plus 16, 32 plus 12 is 44. So I'm in carbon. So carbon to me is a smaller unit. Then I'm going to go to CO2 equivalent. So that's a bigger unit. So I got to multiply it by this value. I got my 12 carbon and I got to convert it over to CO2. So I take my carbon times that number there. Here, once again, you guys, here's the volume equations, carbon equations. Now we can even get into carbon equations directly. We're going to estimate parameters of carbon equations directly. But to me, the carbon values are always going to run off of dry weight. They're always going to run off of tons or volume at some point. And then we're going to use these simple conversions. And then we're going to estimate the parameters, right? But they're always going to run off of volume. And so then we get into questions of where is that carbon? Is it in the mercenable stem, the upper stem? Is it below ground? Is it in the branches? Is it in the foliage? Is it in the litter? Is it in the dead wood? And then you have understory vegetation, even things like mushrooms. Is it in the soil organisms? Where's all that carbon being sequestered? So we have all these different components that you can say of the carbon. And then we have harvested wood products. How much of this do you think we measure directly during any operational inventory? Even in a research setting, we often have indirectly through equations produced from more intensive research, but at a smaller level. The more intensive you get, the kind of the smaller it gets, right? But all of this is running off of the equations, as far as I know. So here's just an example. This is Jenkins. You may have heard of this. This is part of FIA, but they have these Jenkins equations, nanoscale biomass estimators for carbon through, once again, some conversion factor. You have your total carbon. Let's say you're going to use the combined variable. And then how are you going to break it up into these components? Well, I'm going to take this ratio. So I have the foliage, coarse root, stem bark, and stem wood. The total is the sum of all of these. Then I'm going to take some ratio, and this ratio is going to range from 0 to 1. Closer to 1, the more that component makes up of the total amount. The closer to 0, the less or even none of that total is made up in that component. All 4 of these should equal 1, because if they exceed 1 or they're less than 0, whether if they're negative, then that means you're not doing something right, because the total amount of carbon's got to be allocated to some of this component. So you're going to, once again though, you're going to run off of equations operationally. I don't know of anybody that measures foliage carbon directly during an operational inventory. All right, so now we're going to switch gears a little bit and get out of boots on the ground and more into remote sensing. So base map. NCX, land yield, which is core carbon. Anew, if you notice here, information is reviewed via satellite imagery, LiDAR. So this remote sensing, always paired with some type of ground, boots on the ground, and often that's FIA. Once again, everybody, low cost inventory. What's the level of precision that we need given the value of the resource, given what we're willing to buy and sell on? We can kind of break that into whether we're willing to buy and sell on using satellite imagery or aerial photography paired with FIA to infer about how my forest, the amount of carbon being sequestered, stored, or removed in my forest. But you can notice here, NCX, the base map, the satellite, and then core carbon in here, remote sensing. So often this is through some type of, the way I see it is through some type of double sampling. So I have this supplemental variable. The supplementary is the remote sensing. That's the more easily less costly to obtain, the remote sensing. I can estimate the amount of reflectance in that imagery quickly. Then I'm going to pair that through double sampling through boots on the ground, right? That's more costly. That's more difficult. That's kind of really, I'd rather have 100% tally boots on the ground, but I can't do that. So I got a sample on the ground. Probably going to do 100% inventory remotely. But once again, what's the level of precision on that remotely? What's the resolution of that imagery? So The supplementary is the remote sensing imagery, a little easier to obtain, right, because I'm getting a satellite or aerial photography, and then the boots on the ground is more the principle. Remember, through statistical correlation, they're statistically correlated. Then if I know basal area, for example, and it's highly correlated with volume, then a low amount of basal area is a low amount of volume, and a high amount of basal area is a high amount of volume. If I know basal area, I know volume. Here, if there's a weak correlation, I have a small amount of basal area. It didn't tell me any more than if I have a large amount of basal area. I don't know anything about volume if I know basal area, so it's a weak correlation. If I know there's some type of satellite imagery, reflectance, or value that tells me something about the amount of carbon being sequestered on the ground based on the boots on the ground, and therefore I can then infer about how that's going to be throughout the whole part where I don't have boots on the ground, I can use that correlation to my advantage to get a relatively low, inexpensive inventory. Here, we can think of these white as boots on the ground, and here's my satellite image. Okay, you can say aerial photography, but let's just say satellite image or LiDAR. And I have a statewide coverage. What am I going to do? I'm going to measure these plots, boots on the ground, and I'm going to pair some reflected, some aspects, some characteristics of that satellite imagery to that boots on the ground measurement. And I'm going to get this ratio. Then I'm going to come back and I'm going to measure or quantify in the satellite reflectance across the whole state. And I'm going to, in a sense, correct those estimates through these ratio with the boots on the ground. I may stratify this out here versus this here versus this here, more mixed pine, much more pine dominated, delta hardwood. That stratification is going to help me get a little more precise estimate. Nothing different than what we've been doing for years. You get stratification with timber inventories, multiple resource inventories, 3P or whatever, you guys. Same kind of concepts. Once again, everything's going to probably run on diameter and height at some point, and then some carbon estimate through dry weight or so. And then we have the FIA, and in Minnesota they had double intensity. Once again, what's the intensity? How many of these plots do I need? The value of the resource may be so low that this is good enough, but maybe out west, like redwood, or maybe in the delta here, I'm gonna increase. I'm gonna quadruple this, or I'm gonna 10 times this, because the carbon here much more valuable per unit than the carbon down here. Or maybe statistically it's not as well correlated here, so I need a larger sample size. Nothing new in traditional inventories. But Minnesota had the double intensity, meaning they had one plot every 3,000 acres roughly than every 6,000. And you're measuring the boots on the ground diameter and height. And then I'm going to pair this boots on the ground FIA measurements with some satellite imagery. So for instance, NCX, they had Sentinel-2 imagery, and then they split it, I think, kind of stratified it into these eco-region boundaries, so that the relationship between the boots on the ground and the reflectance in Douglas fir, I could kind of pair that out. That way it's not confused or kind of confounded with the reflectance ratio with boots on the ground down with Loblolly pine in the southeast. I'm pretty sure it's not going to be Douglas fir in Florida, at least operation. Now maybe somebody brought one down there, right? So I can kind of stratify out these ecoregion boundaries and use that to my advantage. The climate, all of this went into their inventories. Tree count, stem sizes, they were getting this from FIA. And then through this Bayesian model, prior information, and then updating it through time. To think if they had an idea of what your forest was before, and then they updated it maybe through some ratio with FIA, and then I think at some point they did have some boots on the ground on the back end. But right, as far as I know, never boots on the ground on the front end. So this made for a relatively low cost, inexpensive inventory for the landowner. They didn't have to pay for the inventory. And they were measuring above ground carbon of live trees. They had these equations. They could have estimated equations for below ground, but they were just running off of above ground carbon. Once again, not directly measuring the above ground carbon through equations.